Well, welcome back. We are working now on section 6.5. Now we're getting into the concept of approximating integrals. In other words, you've got this big integral with bounds, and you need to figure out what the integral is, calculate the area under the curve, so forth and so on. The problem is all the techniques that you've learned, use substitution, integration by parts, partial fractions, integration tables, all the things that you've tried, you still can't integrate it because there are functions out there in the universe that aren't integrable. You can't integrate them. So what do we do in those cases? Well, as long as you got bounds, we can go all the way back to the beginning, back to the Riemann sum, and look at some different techniques of Riemann sums to be able to approximate these integrals. So the whole idea here is to approximate these integrals when integration is pretty much out of the book. All the techniques you've learned just won't work for you because it's that hard of a function. Well, the first thing we want to talk about is when you start approximating integrals, you have something called error. And we're defining error to be the true integral, the integral from a to b of f of x dx, the exact value of the area under the curve, the exact value of the integral from a to b of f of x dx minus the approximation. We call that the error of the approximation. Okay. Now, you're familiar with the Riemann sums. We've used left, we used right, we used midpoint Riemann sums, which the midpoint was clearly the best. But you know, there's other techniques as well, and that's what this section's all about. And the first technique of more approximating area under the curves is using the trapezoidal rule. Now, remember the area of a trapezoid. The area of a trapezoid is equal to 1/2 the height times base 1 plus base 2, where you have something like this. This will be base 2, base 1 is at the top, and you've got, here's your classic picture of a trapezoid, and you actually have the perpendicular height h. So to calculate the area of this thing, it is going to equal to 1/2 the height times base 1 plus base 2. Now, when you've got this area under the curve, now let me see if I can draw this thing down here, and you've got some kind of a function here, and what you're going to be doing is instead of putting rectangles under this thing, you're going to be drawing little trapezoids under this thing. So, you know, here's A and here's B and here's some kind of a partition point in the middle. So instead of making, you know, rectangles, we're going to actually make a trapezoid on this thing and find the area of this trapezoid. So remember, this height is the f of a, that's how tall it is. This one will be f of x1, that's how tall it is. This point here would be f of b, and you make a trapezoid, so it's a kind of a straight line approach to this thing. But if you look at this guy and did the trapezoid on this, so the area, remember, the Riemann sum is the sum of the functional value times the height. So to figure out the area of this first little part right in here, this will be 1/2 the height. But if you look at this thing, the height is along this way, because this is your perpendicular distance, and that is a distance of delta x. So your height is delta x, where your base 1 and base 2, because there's really a trapezoid on its side as you look at it from this particular picture here, times f of a plus f of x1. That becomes the area of this first part here. And if I add that to 1/2 the area of the second part, the height, again, this perpendicular distance would have been the delta x distance, because you have to look at it from the side, times the base 1, which will be x1, plus base 2, f of b. So these f of x1s and f of b's, in this case f of a's, these are all your bases. Bases are the height, and your perpendicular, the bases are the f of a and f of x1. The height is delta x on this particular formula. But if you clean this up, you catch a pattern. They all have a 1/2, factoring that out, a delta x. But if you look at what's left over, you'll have f of a, which is your first endpoint, but you'll have 2 f of x1s plus 2 f of x1s plus f of b. So here's kind of your little formula to catch a pattern. But I only made 2 partitions. If I happen to have more partitions, you would extend this out, and this is how we came up with the formula. To integrate from a to b of f of x dx, where a is equal to x naught and b equals xn, as you partition this thing, and your delta x, of course, never changed. It's b minus a divided by n. Then the trapezoidal rule for n partitions is delta x divided by 2. That's your 1/2 delta x, plus f of a, that's your first point, plus 2 times all the internal partition points. 2 times f of x1 plus 2 times f of x2 plus dot dot plus 2 times f of xn minus 1 plus 2 times f of xn minus 2, xn minus 1 plus, and then you got the last point, which is your bound point, f of b. So it's f of a plus 2 times all the internal points, f of the internal points, plus f of b. And that is the pattern for the trapezoidal rule, because when you clean this up, you're doubling all the internals, because the base on one, the bottom base on one trapezoid becomes the top base on the next trapezoid as you move along the partitions and stuff. So, as long as you got the formula memorized, we go to the next problem. So, let us try this problem with this particular question. Let's use n equals 4 and use the trapezoidal rule to approximate the integral from 1 to 3 of 5 over x squared dx. Now, I know you guys can integrate this thing, but that's not the point. We're supposed to use a trapezoidal rule. So as I analyze this piece, a is equal to 1, b equals 5, b equals 3, and my function is f of x equals 5 over x squared. Okay? So a is 1, b is 3, and the function is 5 over x squared. Now, my n, they have to tell me what that is. That'll be 4. So my delta x by formula is b minus a over n. This would be 3 minus 1 divided by 4, or 2 over 4, which is equal to 1/2. So, and what I like to do is, I don't actually draw the function, but I need to draw that x-axis. So here's kind of your y-axis right here, but your x-axis, we're going from 1 all the way over here to 3 on the x-axis, because I got to figure out what my partition points are. My delta x is equal to 1/2. So if I take 1 and add 1/2 to it, that'll be 1 1/2 or 3/2. Add another 1/2 to it, I'm up here at 2. Add another 1/2 to it, I'm at 5/2 or 2 1/2. And another 1/2 to it will make it 3. And you'll notice that I have 1, 2, 3, 4 partitions. So these are my partition points. So remember, the trapezoidal rule for 4 partitions would be delta x divided by 2 times f of a, your first bound point, plus 2 times all the internal points, f of x1 plus 2 times f of x2 plus dot 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 plus 2 times f of xn minus 1 plus f of b, your last point. Now I'm going to plug in my numbers here. So trapezoidal rule for 4 is going to be 1/2 divided by 2 times f of your first point on your partition, which is your bound point, would be f of 1, plus 2 times all the internal points. The internal points would be f of 3/2, plus 2 times f of the next internal partition point would be f of 2, plus 2 times your next internal point, which would have been f of 5/2, plus your last point is your point on the bound. It's 3, so it'll be just f of 3. It's f of the endpoints plus 2 times f of all the internal points of your partition. But now you got to remember that your function is 5 over x squared. So we're going to plug this thing in and clean this up. So the trapezoidal rule, see, 1/2 divided by 2, you divide by a number, you invert multiply, because it's like 2 over 1. That's 1/2 times 1/2, which makes it a 4th. All I did was clean this part up, times f of 1. So I'm going to use my calculator here, but don't really need to here. 5 divided by 1 squared would be 5, plus 2 times 5 divided by 3/2 squared. And I want to show you that I'm literally plugging this in my calculator here, but I'm actually plugging in 3/2 into my function to see what the y coordinate is, which is, I can fraction that, 20 over 9, which is equal to 20 over 9, plus 2 times, plugging in 2, I can do that in my head, 5 divided by 2 squared is 4. 5 divided by 4 plus 2 times 5 divided by 5 halves squared. So plugging on my calculator there, and I end up getting 0.8, and I can convert that to a fraction, 8/10, which is 4/5. Plus plugging in 3. 3 squared is 9, so this will be 5/9. So according to the trapezoidal rule, I'm going to get, and I'm just going to slide it up here and let you see, I'm literally just, this is very calculator friendly stuff here. 1 divided by 4 times 5 plus 2 times 20 divided by 9. Oops, hit the times button. Okay. Plus 2 times 5 divided by 4 plus 2 times 4 divided by 5 plus 5 divided by 9. Close parentheses there. And I end up getting, for the trapezoidal rule for 4 partitions, is 3.525. And that's my solution. Now again, this is an approximation. But let's see how good approximation this guy is. Because we could integrate this thing, the next question we're going to ask you is, let's find the exact value of this guy and then compute the error. Well, the exact value, well, I would clean it up first. This is from integral from 1 to 3 of 5x to the negative 2 dx. This is equal to, integrate, add 1 over add 1. That'll be x to the 5 times x to negative 1 over negative 1, evaluated from 1 to 3. And cleaning it up, this is negative 5 over x, evaluated from 1 to 3. And applying the fundamental theorem of calculus, this will be negative 5 over 3 minus negative 5 over 1. And again, I just want to compare on the decimal version on this thing. So, see what the deal is. So, negative 5 divided by 3 plus 5. And I get 3.333333, which you can clearly see this is the true integral, okay? And it's very, very close. So, what would the error be? Well, the error for the trapezoidal rule would be, remember your formula, it was the integral from 1 to 3 of 5 over x squared dx minus the approximation, and that would be 3.333333 minus 3.525, which is equal to negative 0.1916667. So this is my trapezoidal rule error. Now, will this be the only formula in this particular section? Oh no. Well, there's another formula besides the trapezoidal rule that your professors are going to be teaching you on, and that is, the next one is Simpsons Rule. Simpsons Rule is a combination of both the midpoint and the trapezoidal rule, because honestly, even when you look at the trapezoidal rule on certain problems, it's a good approximation, but the midpoint rule was actually a little bit better. So what they did to come up with Simpsons Rule. Now, Simpsons Rule is a formula, but here's how the formula was derived. The Simpsons Rule is equal to, if you take 2/3 the midpoint rule plus 1/3 the trapezoidal rule. So you're kind of doing this combination of both the midpoint and the trap. If I take the 2/3 the midpoint rule plus 1/3 the trapezoidal rule, that gives me Simpsons Rule for twice the number of partitions. Okay, and because it's based upon twice the number of partitions, we always, when we're doing this particular rule, we always say that the partitions have to be an even number. You have to have an even number of partitions. N equals 4, 6, 8, okay, so forth and so on. You've got to have an even number of partitions because it's a combination rule, and because when you combine these two formulas, you get Simpsons Rule, the better approximation for the integral. So Simpsons rule, you take delta x divided by 3 plus f of your endpoint plus 4 times f of your first internal point plus 2 times f of your next internal point plus 4 times f of your next internal point. So you got this endpoint plus 4, 2, 4, 2, 4, 2. And because it's even, you'll always end on a 4 just before your other endpoint. Your endpoint's based on the integral between a and b. So it's always f of a plus f of b, right off from the trapezoidal rule, but it's a 4, 2, 4, 2 combinations in terms of the internal points. And remember, you always start on a 4 and you'll end on a 4 on the internal points just before your endpoints. And that always works when you have an even number of partitions. So this is a requirement. To do the Simpsons rule, you have to use an even number of partitions. So let's take a look at this guy here. The question: use n equals 4 to Simpsons rule to figure out the integral from 0 to 1 of e to the x squared dx. Well, here we go. Now, to do this particular integral, first thing I would just want to point out, the integral of e to the x squared is not a function you know how to integrate. I mean, you know how to integrate e to the x, granted. Integral e to the x is e to the x, but this is not e to the x. This is integral e to the x squared. And this is actually one of the functions out there in the universe that doesn't have an antiderivative. You officially can't integrate this. All you guys have TI-89 calculators that want to sit there and use the integral button on it, yeah, knock yourself out. When you integrate e to the x squared dx, it gives you the question right back in the answer because it can't do it. There is no integral for e to the x squared. There are functions out there like this, and that's why we're teaching this numerical approximation method in chapter 6.5. How do I integrate this guy? Well, we're going to use Simpsons rule to approximate it because that's the best we can do is approximate it. So my function of f of x is equal to e to the x squared. My a is equal to 0. My b is equal to 1. And n equals 4, which makes delta x. Well, by formula, it is b minus a over n. That'll be 1 minus 0 divided by 4, or 1/4. Just like I did with the trapezoidal rule, I don't actually have to draw out the function, but I definitely have to draw out the x-axis because I need to see what my partition points are. My bounds are between 0 and 1, but my delta x is equal to 1/4. So I start with 0 and I move over 1/4. I move over another 1/4, which makes it 1/2. I move over another 1/4, which makes it 3/4. I move over another 1/4, and I'm at my endpoint 1. 4 partitions, 1, 2, 3, 4. So these are my partition points. Again, Simpsons rule. The formula is delta x divided by 3 to calculate Simpsons rule. And that's times f of a, and you start out with your endpoint, f of a, plus 4 times your first internal point, x1, plus 2 times your next internal point, plus 4 times your next internal point, plus 2, 4, 2, and you end up on a 4 times your last internal point just before your endpoint. That's my formula. It's always a 4, 2, 4, 2, 4, 2, but you end up on a 4 on the internal points just before the last endpoint. So my Simpsons rule, and remember, n had to be even, but 4 is even, so we're good to go on using Simpsons rule on this one. So Simpsons rule for 4 would be equal to delta x, which is 1/4, divided by 3, times f of 0, plus 4 times your first internal point, which is 1/4, plus 2 times f of 1/2, plus 4 times f of 3/4. But you'll notice 3/4 is your last internal point before your endpoint, plus f of 1. Okay? So cleaning this up, this is going to be equal to 1/4 divided by 3. That is equal to 1/12 times f of 0. But remember, f of x, you're not actually integrating this thing. F of x is e to the x squared. That's what we're trying to integrate. So this would be e to the 0 squared plus 4 times e to the 1/4 squared plus 2 times e to the 1/2 squared plus 4 times e to the 3/4 squared plus e to the 1 squared. And I'm going to use the powerful TI, I've got an 84 up here. So here we go, using my T84. This would be, always put parentheses around fractions, 1/12 times, parentheses, e to the, I'm typing it in just to show you guys, 0 squared plus 4 times e to the, another parentheses around these fractions and the exponent, 1/4 squared plus 2 times e to the parentheses 1 divided by 2 1/2 squared, and you'll notice I have to hit over arrow on this thing to get it to put my closed parentheses there for that point, plus 4 parentheses e to the parentheses 3/4 squared, close parentheses, plus the last one, which is just plain old e to the 1 squared. But then I have to close parentheses for all my terms here. So before I hit enter, I just want to show you that I'm actually typing this thing in exactly the way it looks. That's the beauty of the Texas Instrument Calculator here. Okay, but, and this is also because you're going to get some nasty looking functions up here. This is where most people, is because it becomes a calculator problem, but this is where most people will make their careless errors at. So this is exactly what I'm supposed to have. And I look at this thing that I typed it in correctly, and then I hit enter, and it tells me my answer. So for the Simpsons rule, for 4 partitions of the integral from 0 to 1 of e to the x squared dx, I got 1.46371076. Just to let you guys see it. 1.46371076. Because now, how do I figure out the error on this thing? Well, we're going to be doing some calculator projects and the like on this, and this is a calculator style project because you do have that integral button on that calculator, and we're going to use it. We want to figure out what the error in the Simpsons rule is, and remind you about error. Error for the Simpsons rule would be the integral from a to b of f of x dx minus the approximation. Well, what do we get with this particular integral? Well, we're supposed to use the calculator to find this guy. So I'm going to remind you guys on how to use the calculator. For this is for a T84. If you've got an 89, it's a similar keystroke, but you have to, it's above number 7. But this is the T84. You go to Math, scroll down to Math number 9, FNINT. But with the new upgraded T84, I actually have the bounds on mine. If you have the old one, it'll be old 84. It'll be FNINT. You type in the function, comma x, comma low bound, comma upper bound. But for ours, we're just going to type in the function. Integral from 0 to 1 of e to the x squared dx. That's what we were supposed to integrate. In this particular problem, just want to remind you what the original question was. So I typed it in exactly the way it looks, and the calculator gives me this. So my error for Simpsons rule would be the integral based upon the calculator, 1.46251746, no rounding on the decimals here. My approximation that we calculated on the previous page was 1.46371076. So when I subtract these two guys, I end up getting the error for the Simpson rule would be a negative 0.00105904141. Now the last little bit behind this is, what does this mean? Simpsons rule is the best type of approximation you can do with this type of stuff because it combines midpoint rules with trapezoidal rules. But here's the deal, and understand why this is important. I only used 4 partitions. N was equal to 4. That's not a whole heck of a lot of number of partitions here. But the difference between the true integral and the approximate integral with n equals 4 partitions is 0.001059014. .001. That is actually automatically correct to 2 decimal places on this thing. That is an excellent approximation with fewer partitions. That's the whole purpose of this stuff. How do I get a great approximation with as few partitions as possible? Because I can't actually integrate certain problems out there. So hopefully this has been helpful, and I'll see you in the next video.